those the Cauchy inequalities, the one from the Losfield theorem.
Mm-hmm.
But then it's kind of another thing. And then
Okay, so essentially what you do is this. Okay, so F is like U plus IV, right?
Mm-hmm.
And you know that the imaginary part's a constant, right? So basically it's U plus IC.
Mm-hmm.
Okay, now the Cauchy-Riemann equations. Okay, so Ux is Vy and Uy is negative Vx. But V is just a constant, so these are going to be 0, right?
So U also be 0 too. U is also constant too.
Yeah, so those are gonna be 0, okay? So you get that. So those are gonna be, so that means that U is also a constant. We'll call it V. But that's only on the closed unit disk. That's only on the closed unit disk. This is the closed unit disk, okay? So to get everywhere else, what you do is use the fact that it's entire and do this. Make G of Z equal to F of Z minus B plus IC. Okay, so G of Z is on the unit disk. What's G of, is going to be 0 on the unit disk, right?
Mm-hmm.
So then so you have that 0 on the unit disk, right? So then, and also G is entire, and it's 0 on the unit disk. So then look up the identity principle. Wait, I have a problem spelling that. Identity principle. Yeah, so look up that and see what that says about that, okay?
Okay.
So that will help you with that problem.
Sounds good.
Sure, you're welcome.
Mm-hmm.
I'm trying to figure out what else I'm supposed to do today. Okay, here we go. Okay, let's take a look at exercise number 37. I hear 37. So this is on the assigned homework, right? So that's on the assigned homework. I'll just give you some hints on how to do it. So what you can do is expand this. Expand it about -1. Okay. So in other words, you have to try to find these constants here. Okay, you can try to do that. That might not work. That might not work out too well. And you might be able to figure it out, maybe not. Okay, but really, the only one that matters is hold on a second. If we divide by, hold on, I'm sorry. If we divide by z plus 1 to the 34th power, then all these are going to be over z plus 1 to the 34th, right? So the only one that matters would be, let's see, if this is 33, then it's going to be z plus 1 to the 33rd power over z plus 1 to the 34th. So that's just going to be this. That over that. Okay, and so the integral is going to be 2 pi I times whatever that one is. That's going to be the integral. So you just have to figure that out. This. You don't have to figure all the values out. Just that one, what's C33? Okay, and that is because of this corollary 827. Let me show you right here. This corollary right here, which I think we talked about this a little bit. So if your function is expanded like that in a Taylor series or a Maclaurin series, no, I'm sorry, in a Laurent series, then the integral is going to be 2 pi I times c minus 1.
What exactly is c minus 1?
What's that?
Yeah.
Okay, so c minus 1 is the coefficient above the okay, so here, what this means is that your function can be, it's going to be like this, dot, 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 plus c minus 2 over z minus z naught squared, plus c minus 1 over z minus z naught, plus c0 plus c1 times z minus z naught, and so on. Okay, so it goes that way infinitely and that way infinitely, potentially.
Mm-hmm.
And so what this theorem is saying is that this is the only one that's relevant right here. This coefficient right here, the c minus 1 term. The one that's over the z minus z naught. Now, over here, what I've done over here is I started out wrong. I should have, and I was just saying exponentials are, the exponential function is c0 plus that. But maybe what I should have done was gone more like this. It would be c negative 34 over z plus 1 to the 34th power. Okay, plus c negative 33 over c plus 1 to the 33 power. And gone like that. And so then we have c minus 1 over z plus 1. Okay? And so on. But this is the one that you want to focus on. And you do it by expanding out the exponential. I wouldn't mess with that one because that can be, well, I guess you can multiply both sides by that and then use it to find that. Okay.
Okay.
So that's something that's gonna come up a lot. We'll do some more exercises like that next section. I want to also give you an idea about how to do number 32. So this one right here. So here it says in 3 regions. Okay, so it's hint use partial fraction decomposition. So what's going to happen is you'll do partial fraction decomposition, right?
Mm-hmm.
Like that. So that's the first step. Find this A and B, and then you got that like that. Okay, now this one is going to have two Laurent series. We talked about that before. This one's going to have two also. Two Laurent series. Let me give you an indication of what that's going to look like. Okay, just with this one. Okay, so let's suppose we had 1 over z plus 1. No, z plus 2. I'm sorry, because it's z plus 2, right? Okay, so one Laurent series would be the Taylor series, and the idea is to manipulate it into something like this. Okay, 1 over 1 minus something. Okay, here we have 1 over 2. We can do 2 plus z, right? You can just flip those and get a 2 there. And then, but you can also, you can have like a constant out here. You can have something out here. Okay, and I guess the main key is just to get a 1 right there. That's the main thing right there, and that's the main focus, is getting a 1 right there. That's the main thing. Okay, because if you do that, then everything else falls in place. Okay, and then a minus here. Okay, so if we divide the numerator and denominator by 2, then you'll have a 1/2 in the numerator, and you'll have a 1 plus z over 2 in the denominator. Okay, and then that's going to be 1/2 over 1 minus. You can make it a minus, but then this is going to be negative z over 2. Okay, and then that is just going to be this Taylor series. Okay, and this will converge when this is less than 1 or modulus z less than 2. So you got that. Okay, now for the second one, you get the 1 right here instead. But this is, I'm gonna divide by 1 over z. I'm gonna divide by z, the numerator and the denominator. So the numerator is just gonna be 1 over z. Distribute this in here, you get 1 plus 2 over z. Okay, so that's gonna be 1 over z times 1 over 1 minus a negative 2 over z. And this one is going to be 1 over z. Wait, let me back up a little bit. Okay, so this one is going to be 1 over z times the series negative 2 over z to the kth power. Okay, and we can split that up, and the denominator is z to the k, but you have this other z, so you can say z to the k plus 1. Like that. And this one converges when modulus of 2 over z is less than 1, which translates to, what's an or? To modulus of z greater than 2. Okay, so you have two different series. One converges for modulus of z less than 2, and the other one, this one, converges when modulus of z is greater than 2. And they both represent They both represent 1 over z plus 2, both of these series, but on different places, in different areas, different regions. Okay.
When I was doing the homework, I realized that some of the Lorentz series doesn't have a Taylor series inside, doesn't have a series inside. Is that like, can the Lorentz series just be constant, or not a summation?
What is that? What is that? When you're doing the homework, what happened?
I think there's one problem that the answer is not a summation of something. It's just
oh, okay. That's okay. If you put down the first 3 or 4 non-zero terms, that's fine. But sometimes it's just too hard to find a formula. So this is like, here's a formula, right? And here's a formula. Sometimes it's just too hard to find a formula. Okay. So here's what you're gonna do. So here is, I have this 1/2 out here. Oh well, that's okay. So here you got one formula, and you got the second one. Okay.
Mm-hmm.
So so what happens is, for this one, you're also going to have a 1 and a 2. And this one will converge for modulus of z less than 1, and this will converge for modulus of z greater than 1. Okay, and then from the other page, okay, so from next page, this one also has a 1 and a 2. Okay, and so 3 regions, here's what's going to happen. You have 3 regions, modulus of z less than 1, modulus of z between 1 and 2, and modulus of z greater than 2. Okay, so now this one only converges in modulus of z less than 1. And these two, this one converges when modulus of z is greater than 1. So it converges, so the second series for this one converges there and there. Okay. This one, the first one converges for modulus of z less than 2. So that means that one converges here and here. So that series there. And then this one, the second one converges for z greater than 2. Okay, so those are going to be your 3. Those will be your 3 answers. 1 plus 1, the first one here plus the first one there, which you can get by following what's on the next page. This one would be number 2 and number 1 still, and then this last one will be 2 and 2. Okay, so the second series and the second series. Okay, one other thing that I want to do, well, is I want to do an example of this, finding multiplicities of zeros of functions. So just to give you an idea of how to do that. So let's go z. So let's have this function right here, z minus 2 squared times exp of z minus 1. And then for good measure, I'll throw in a, let's see here, z. to the fourth power. Okay, so the question would be find the zeros and their multiplicities. Okay, so can you name any zeros of this function?
Yeah, 2, 0, and 1.
And one's not a zero.
Oh, 0.
Was that doesn't
yeah.
one makes it e minus 1. Okay, so but this is the tricky part. What's the multiplicity for 2? Well, that's just going to be 2 for this power here. Okay. Also, believe it or not, we haven't. That's not all the zeros. Can you think of any more?
2k pi.
What's that?
2k pi.
2 pi?
Pi k.
Okay, actually it's 2 pi I. Okay. Okay. Now, these ones are just multiplicity 1. I'm not going to get, because these values here make the exponential function equal to 1. Okay, so e to the 2 pi I, remember that's cosine 2 pi plus sine 2 pi. And so that's going to be 1, because this is, and that's going to be 0, because this is coterminal with the angle 0. So it's like putting a 0 in. Okay, so that's 1, for example. And if you have a multiple of that, then that's also going to be 1. Okay, now this 0 here, you have over here, it's to the fourth power, right? This is actually, and this actually adds 1 to it. So this is actually going to be 5. Okay, that's going to be multiplicity 5.